Okay, this is exam 3 for spring of 2009. The first one, it says a mirror produces a virtual image that is upright and has a magnification greater than 1. What kind of mirror is it? Well, it's a virtual image, so that could be either concave, convex, or flat mirror. But the fact that it has a magnification greater than 1 means that it can only be a concave mirror. This is like a shaving mirror or a magnifying mirror like you have in your bathroom. So the answer for this is B. A convex mirror, by the way, that's like you have in a convenience store, a security mirror, and that has a magnification less than 1. And a flat mirror has a magnification equal to 1. Images made by mirrors are affected by which of these aberrations? Well, mirrors are affected by spherical aberrations. Mirrors are not affected by chromatic aberration. That's only for lenses. For mirages are not an aberration, and photographic aberration, that's just made up. So the answer is B. A camera can be modeled as a simple converging lens that focuses an image on the film acting as the screen. A camera is initially focused on an object just outside the focal length. To focus the image of an object very far from the camera, the lens must be what? Well, initially you have an object that is just outside the focal length. So here's my lens, this is the screen, here's the focal length. My object is just outside the focal length. Now, the image is going to be projected onto the screen, is going to be projected behind the focal point. I can draw some rays to show that. So the image of this object is behind the focal point. But if I have an image, or rather an object, that's very, very far away, that means that it's going to focus at the focal point. So my image, if my object is very, very far away at an infinite distance, that means that the image is going to be at the focal point. That means that your screen or your film has to be moved there. So to focus the image very far away from the camera, the lens must be moved toward the film. That's A. This is a very similar question, though instead of changing the distance between the lens and the film, here you're actually changing the focal point or the focal length of the lens, and that's the human eye. So in the human eye consists of a lens, a convex lens or a converging lens, and the screen is on the back of the eyeball, which is the retina. Now you can't change the distance between the retina and the eye. That's just set by the size of your eyeball. However, there are muscles inside the eye that can change the shape of the lens, and that changes the focal length of the lens. Now here, initially, you're focusing on something that's very far away. So here is your lens of your eye. You have light rays that are coming in parallel from an object that's very far away, and that's going to focus at the focal point. Alright, so our lens is, or rather our retina is going to be at that point. Now I want to focus on something that is much closer. And if I'm focusing on something much closer, I want to know, how does my focal length change? Now the distance between the lens and the retina does not change. However, we can change our focal length. And in this case, our focal length is going to get smaller in order to produce an image that's still at the same point on the retina. Alright, so the focal length going from this point to this point is going to decrease. That's option A. Which of these four rays is drawn incorrectly for this diverging lens? Well, this first one goes parallel to the axis, and then it goes such that if you traced it back, it would go through the focal point. That is correct. The next one goes in this direction such that if you were to trace it forward, it would go through the focal point, and then it goes parallel to the axis. That is correct as well. The next one goes straight through the center of the lens. That is correct. And let's say D goes through the focal point and then parallel to the lens. That is not correct. Actually, if you were to trace this one, it would go something like this, way out in the middle of nowhere, because it's a diverging lens. Alright, one way that you can test this is that you can trace all the rays back. We know that this is going to produce a virtual image. So if I trace these rays back, my image is going to be right here. However, if I trace this ray back, it doesn't come anywhere close to that. So option D is the one that is incorrect. You could have different kinds of lenses or mirrors on this, any of the ones that we discussed in class. At an intersection of a hospital hallway, a convex mirror is mounted high on a wall to help people avoid collisions. The mirror has a radius of curvature of 2 meters. So the radius of curvature is 2 meters. It is a convex mirror, so we would say that that's -2. This is like a security mirror, so the radius is behind the mirror. And the focal length is half of that radius of curvature, or -1 meter. Alright, what is the magnification of a patient 5 meters from the mirror? So P, that is the object distance, is 5 meters. And we want to know what is the magnification. Alright, magnification is equal to minus Q, that's the image distance, over the object distance. So we know what P is, the object distance. We just need to figure out what is Q. We know F and P, so we can use the mirror equation. That is that 1 over F equals 1 over P plus 1 over Q, and solve this for Q. So Q is equal to 1 over F minus 1 over P. The inverse of that, that is 1 over -1 minus 1 over 5. That gives me a Q value equal to -5/6. Alright, so I can put that in over here. I get -5/6 divided by P, which is 5. That's +1/6, which is 0.16. So the answer is A. A 2 centimeter high object is placed 2 centimeters in front of a concave mirror. If the image is 4 centimeters high in virtual, what is the focal length of the mirror? This is a concave mirror. This is like your shaving mirror. And here you have a virtual image, and a virtual image and a concave mirror is upright. When it is magnified. This is like looking in your magnifying mirror. Right? Your face doesn't look upside down when you're up close to it. It's upright. So our virtual image is upright. So I can write some of the things that we have here. Let's see, the height of the object is 2 centimeters. The height of the image, called H prime, is 4 centimeters. And since it's upright, that's going to be +4 centimeters. Let's see, the object distance, P, is 2 centimeters. And I want to know what is the focal length equal to. Well, in order to find the focal length, I need to know the image distance, because I know that the 1 over the focal length equals 1 over Q plus 1 over P. I have P, so I need to find Q. So I can find that from the magnification. The magnification you can find in 2 ways. The image height over the object height, which in this case is 4 centimeters over 2 centimeters, which gives us a magnification of +2. But you can also find the magnification by minus Q over P. And that's going to also equal +2. So I can use this to solve for Q, and I find that Q is equal to -4 centimeters. So my image distance is -4 centimeters. That makes sense. Since it's a virtual image, Q should be negative. Alright, so I can take this and plug it in down here and solve for F, which is 1 over Q plus 1 over P. That's 1 over -4 plus 1 over 2. This gives me a focal length of 4, which is option D. In this image, the smiley face sees an image of the heart in a flat mirror. Where does smiley see the image of the heart? Well, for a flat mirror, the image distance is equal to the object distance. So this is P, and this is Q. P is equal to Q, so it has to be B. What is the final position of the image created by this set of 2 lenses? Okay, let's see. My focal length for this first one is right about here. I want to find what is the object distance for the first lens. So I'm going to work this in 2 ways. P in 2 steps. P1 is equal to 30 centimeters. That's the object distance. The distance from here to here is 30 centimeters. F1 is 15 centimeters. and I want to know what is Q1 equal to. And Q1 is equal, using the lens equation being 1 over F equals 1 over P plus 1 over Q. If I solve that for Q, it's 1 over F minus 1 over P. And putting in these values for F and P, I find that Q1 is equal to 30 centimeters. That means that I'm going to produce an image right about here. That image is going to become the object for the second lens. So this distance from here to here, I'm going to call P2. So P2 is equal to 70 minus 30, because I know that this distance is 30 centimeters. This distance has to be 40 centimeters. F2, we're told, is 20 centimeters. And then I just solve for Q2 in the same way as I did before. That's 1 over F minus 1 over P. And that gives me a Q2 equal to 40 centimeters. Okay, it's a positive value. That means it's on the right side of that lens. So it's 40 centimeters to the right of lens 2. That's C. If it worked out to be negative, it would be to the left. That would be a virtual image and not a real image. It would be a negative value, meaning that it's on the same side as the object for the lens. So 40 centimeters to the right. Chromatic aberration is caused by which of these? The direct reflection of different colors of light. That's not true. Chromatic aberration is due to the refraction of light. Different parts of the lens or mirror focusing light at different focal lengths. That's not true. That's actually a spherical aberration. The effect of chroma on the aberrant light, that's just made up. And the wavelength dependence on the index of refraction, that is true. Chromatic aberration, if you have blue light that comes in, it focuses at a certain point. Then, if you have red light that comes in, it's going to focus at a slightly different point, because the index of refraction for those particular colors is different for a given material. So it's wavelength dependent on the index of refraction. What causes a mirage you see while driving on a road? Alright, well, it's the refraction of light in warm air. We discussed this in class. The others are wrong. Well, let's see. The reflection of light from the atmosphere, that's not true. Neither one of these are true. Most cameras have an aperture to block the outer edges of the lens. What is the purpose of this aperture? It's to reduce the effects of spherical aberration. Spherical aberration occurs when you have light rays that come in on the outer parts of the lens and they focus at a certain point, and then light rays that come in on the inner portion of the lens and they focus at a certain point. Because you have these different focal points, they produce a fuzzy image. So you mask out these outer regions to get rid of this focal point, and so most of the light is going to focus at the focal point from the inner region. Which of these mirrors will produce a virtual image under particular conditions? Well, the flat mirror always produces a virtual image, as does the convex mirror always produces a virtual image. The concave mirror likewise will produce a virtual image when you're inside its focal point. So the concave mirror also produces a virtual image. So the answer is A. Alright, a laser beam is incident on two slits, so this is a double slit, that are separated by 1/10 of a millimeter. How far is the second bright fringe from the central maximum? Well, we start with this. D sine theta equals m lambda. Noting that m is for the bright spot. I'm going to put in some numbers. 0.1 times 10 to the minus 3 meters is d sine of theta is equal to 2 times 650 times 10 to the minus 9. That's in meters. And then I solve for theta. My calculator should be in degree mode. Theta is 0.745 degrees. In general in this course, your calculator will need to be in degree mode. I'll try to make it very clear when it needs to be in radian mode. So anyway, theta is 0.745. So I'm going to sketch this out. Here's your two slits. Here are your two slits. And then this is the diffraction pattern that you get. and I want to know the distance from here to the second bright fringe. That's the first to here. I want to know what is this distance. I'm going to call it y. We've already solved for the angle. This is the angle theta that we solved for, and we know that this distance is 5 meters. Now the tangent of theta is opposite over adjacent. That's y over 5. So y is equal to 5 tangent of theta. 5 of tangent of 0.745, and y is equal to 0.065 meters. That is 6.5 centimeters, so that's option A. Alright, helium neon light is sent through a 0.2 millimeter single slit. What is the difference in angle between the first dark fringe and the third dark fringe? Draw a picture over here. I like to draw a picture. Alright, I want to know the angle between the first and the third dark fringe. This is the first fringe. This is the third fringe. I'll call this theta 3 and this theta 1. Alright, where theta 1 is this angle and theta 3 is this angle. Alright, and note that the order here, that this is m equal 1 and this is m equal 3. When you're dealing with a single slit, the order number m refers to the dark fringe. When you're dealing with a double slit, the order number m refers to the bright fringe. Alright, so we're dealing with a single slit, so m refers to the number of the dark fringe, the order for the dark fringe. So then I just want to solve for theta 1 and theta 3 and then take the difference between them. I know that a sine theta equals m lambda, and I just want to solve for theta. It's the inverse sine of m lambda over a. That's the inverse sine for theta 1 of 1 times 632.8 times 10 to the minus 9 meters divided by a, which is 0.2 times 10 to the minus 3. And that is equal to theta 1, which is 0.181 degrees. And then in a similar way, theta 3, which is the inverse sine of 3 times 632.8 times 10 to the minus 9 divided by 0.2 times 10 to the minus 3, that is equal to 0.544 degrees. And then the difference between those, 0.544 minus 0.181, is equal to 0.36 degrees. So that's the answer A. Alright, a spectral line occurs at 30 degrees in the second order spectrum of a diffraction grating spectrometer. The wavelength of this spectral line is 600 nanometers. How many slits per millimeter are on the diffraction grating? Well, the same equation that we use for a double slit applies to a diffraction grating. That is that d sine theta equals m lambda, and d is the separation between the slits on the diffraction grating. So I want to figure out what is d. D is equal to m lambda over sine theta. Then we need to figure out what these numbers are. M is the order number, that's 2, second order spectrum. Lambda is 600 nanometers, 600 times 10 to the minus 9 meters, divided by the sine of theta, 30 degrees. That gives me 2.4 times 10 to the minus 6 meters. That means that there are 2.4 microns separation between the slits on this diffraction grating. But I don't want to know that. I want to know what is the number of slits per millimeter. So I want to take, this is the number of meters per slit. I want to take the inverse of this. So 1 over 2.4 times 10 to the minus 6 will give me 4.17 times 10 to the 5th. That's in slits per meter. But then I want to convert that into slits per millimeter. So I'm going to write it down here, 4.17 times 10 to the 5th slits per meter. In 1 meter there are 1,000 millimeters, and that gives me 417 slits per millimeter, which, keeping proper sig figs, is 420. That's option D. Alright, if a wave from one slit of a Young's double slit setup arrives at a point on the screen one wavelength behind the wave from the other slit, what is observed at that point? Alright, so let's say we have these two waves. There's your one wave. This is a wavelength. So they're going to be separated by a wavelength. Alright, but when they're separated by a wavelength, the peaks still line up with the peaks, and the troughs still line up with the troughs. So see, these are separated by one wavelength, as is in this. But when you're separated by one wavelength, you still get a bright fringe. It's because you still get constructive interference. In a Young's double slit apparatus, by what factors the angle between adjacent light and dark fringes changed when the separation between the slits is doubled? And you assume the small angle approximation, that is that sine theta equals theta. Well, for a double slit, we say d sine theta equals m lambda, but we're making this approximation that sine theta is equal to theta, so d theta equals m lambda. If we double the slit width, d, then that's going to halve the angle. So the answer is C, 1/2. Waves from a radio station with a wavelength of 600 meters. So the wavelength of 600 meters arrive at a home receiver a distance of 50 kilometers away from the transmitter by two paths. One is a direct line path, the gray line, and the second is it's a reflection from the mountain directly behind the receiver, which is the black line. What is the minimum distance between the mountain and the receiver such that the destructive interference occurs at the location of the listener? So in order to get destructive interference, you need a difference in path length by a half a wavelength. So the total difference in path length, I'll call that delta L, has to be a half a wavelength, which in this case the wavelength is 600 meters, so it's 300 meters. So half a wavelength path length difference. At this point, they've traveled the same distance. They've traveled 50 kilometers. I need an additional path length of 300 meters. All right, so it's going to travel 150 meters and then another 150 meters to give me a total of 300 meters. All right, so that means that this distance has to be 150 meters, which is D. This figure shows an interference pattern produced in the double slit experiment. What is the path length difference of the two waves that formed the bright fringe as indicated by the arrow? Well, here we have 0 path length difference. Here we have a path length difference of 1 wavelength. And here we have a path length difference of 2 wavelengths. So the answer is 2. Consider the superposition of these two waves. Which of the choices represents the interference pattern? Well, these two parts are going to cancel out. So you're just going to be left with a straight line. These two parts are going to add constructively, so they're going to double in size. And then part of this is going to add up, and part of it's going to cancel out. This part is going to cancel with this part, and this part is going to cancel with this part, but this is going to add up with this. So you're going to be left with a big spike there. So that is option A for number 21. Helium neon laser light is sent through a single slit of 0.3 millimeters. What is the width of the central maximum on a screen 1 meter in the back of the slit? So remember, I'm drawing my picture over here. Here's my single slit. This is m equal 1 on either side. This is my angle theta 1. I want to know what is this distance. So I first want to figure out what is the angle theta. A sine theta equals m lambda. Solve that for theta. That is m is going to be 1. Lambda is 632.8 times 10 to the minus 9 divided by A, which we're told is 0.3 millimeters. That's 0.3 times 10 to the minus 3 meters. and that angle theta works out to be 0.12 degrees. Alright, now, so that's my angle theta. I'm going to draw a triangle over here. This is the angle theta. I'll call this distance y and this distance L. Y is equal to L tan theta based on the definition of the tangent of theta, that is its opposite over adjacent. And this is equal to 2.1 times 10 to the minus 3 meters. Alright, that is this distance, which is just half the width of the bright fringe. So what I really want to know is 2y, which is 4.2 millimeters. 4.2 times 10 to the minus 3. And that is the answer A. Alright, which of these phrases best gives the meaning of coherent as it applies to light? Alright, the best meaning of coherent here is C. Alright, that it maintains a fixed wave relationship. Alright, two waves are initially in phase and have a wavelength of 0.5 meters. One wave travels 3 meters and another wave travels 4.25 meters. What is soon when the waves recombine? The issue here is what is the path length difference? And how is it an interval or an increment of the wavelength? So our path length difference is 4.25 minus 3. That's 1.25. And the wavelength is equal to 0.5 meters. Alright, so 1.25 divided by 0.5 is equal to 2.5 wavelengths. So since you have this half wavelength increment, it's going to be a dark spot. If it was 2 wavelengths, it would be a bright spot. If it was something in between, like 2 3/4 wavelengths, it would be a gray spot that is neither dark nor bright. Okay, light of 500 nanometers is incident on a double slit of width 1000 nanometers. What is the highest order present in the diffraction pattern? Well, d sine theta is equal to m lambda. It's for double slit. And the highest order occurs when theta is equal to 90 degrees, because this is the angle theta. It just can't exceed 90 degrees. When it's at 90 degrees, it's over here, and it can't exceed that. So this becomes 90 when the sine of 90 is just 1. So d is equal to m lambda. We want to know what is m. So that's d over lambda. D is 1000, lambda is 500, so that's 2. 1000 over 500 equals 2. That's B. Alright, and these two waves, the peaks line up with the peaks and the troughs with the troughs, is in phase. That is A and B.